Welcome back. So far we've been looking at the connections between renewal theory and DTMCs. All right. In particular, we have said that consecutive returns to a particular state, recurrent state J, constitute renewal instances. Today we are going to use renewal theory, renewal reward theory in particular, to discover the stationary distribution of a countable state DTMC. All right. Recall that we say that let us say a PMF pi is given to you, all right. So, this sum over pi I equals 1, okay, such that it satisfies pi I equals sum over pi j p j I, okay. Suppose a PMF on the states satisfies pi I is equal to sum over j pi j p j I, all right. Then we can show that if the chain is started in the distribution pi, then for all I belongs to S, then probability that xn equals I will also be equal to pi I for all I belongs to S and for all n greater than or equal to 1. What does this mean? We already saw this in the finite state context. So, essentially we are saying that pi is equal to pi p, except that I am not writing it as pi is equal to pi p, because the matrix P is not really a matrix now, it is an infinite dimensional object. But the fact remains the same, that if you start off the Markov chain at time equal to 0 in state I with probability pi I, then the probability of being in state I for any time n remains pi I for every state I. Okay. This is easy, this is just by applying total probability and Markov probability, all right. Now, the thing is, we are going to prove that this stationary distribution, if it is such a pi PMF pi is known as a stationary distribution. This we have already seen of the DTMC, right. Such a PMF such a distribution is known as the stationary distribution of the DTMC. Now, we are going to relate this pi, if at all there exists such a pi, we are going to relate it to recurrence times, okay, mean recurrence times of state I, okay, using renewal theory, renewal reward theory, okay. So, this the key result is the following, okay, theorem. So, theorem 1, consider an irreducible countable state DTMC for which pi I satisfies the star, right. Then let me write the following. Then number 1, the chain is positive recurrent. The solution pi is a unique solution to star, and further pi I is equal to 1 over expected TII for all I in S. Okay. So, this theorem is a very important theorem, right. Suppose, so it says that suppose you manage to find a solution pi, all right. Suppose if somehow by guesswork or asking somebody or whatever means you manage to find a solution, a distribution pi such that sum over pi i's are equal to 1 and sum over j pi j p j I is equal to pi I, right. So, these are the balance equations, this is what we call the global balance equations. So, if you manage to find a solution to the global balance equation by whatever means, then we can come to some important conclusions. Okay. The conclusions are that the solution you manage to find is unique, okay, and the chain is positive recurrent, and furthermore the pi i's you found out are the reciprocals of the mean recurrence time of each of the states. Okay. So, there are 3 conclusions in this theorem, all right. So, you somehow managed to find a pi I. So, this theorem says that A, this chain is positive recurrent, B, the solution you managed to find somehow is the only solution, there cannot be any other solutions to pi is equal to pi p, and this pi I has the interpretation as the reciprocal of the mean recurrence time of that particular state. Okay. So, this is a very important theorem. Okay. Let me also state theorem 2, which is like the converse of theorem 1. So, these 2 theorems are central, okay, and then we will see how these theorems are proved using renewal reward theory. Okay. Suppose an irreducible countable state DTMC is positive recurrent, then star has a solution with pi I is equal to 1 over expected TII for all I in S. Okay. So, this is like the converse, theorem 2 is like the converse. Theorem 1 says that if you somehow manage to find a solution to this pi is equal to pi p, to these balance equations, then you get positive recurrence for free and the solution is unique and pi I will be equal to 1 over TII bar, right, expected TII for each state. Now, we are saying the opposite, right. So, now I do not know pi, all right, but I know that the chain is positive recurrent, all right. So, what I know is that, so it is an irreducible DTMC, it is positive recurrent, right. So, all states are positive recurrent. So, 1 over expected TII bar is something non-negative, it is actually strictly positive if you think about it, because expected TII is finite, right, because it is positive recurrent. So, 1 over expected TII is some strictly positive number, right. We are saying that 1 over expected TII is a solution to pi is equal to pi p, okay, that is what theorem 2 is saying. Okay. So, these 2 theorems can be viewed as I mean theorem 2 is a converse to theorem 1. Okay. So, positive recurrence implies there exists this 1 over TI bar is a solution to pi is equal to pi p, and theorem 1 says if pi is equal to pi p has a solution pi, then it is unique, positive recurrence follows, and this pi has the interpretation of 1 over expected TII. All right. So, bottom line is that the stationary distribution pi I for any positive recurrent Markov chain is simply 1 over expected mean recurrence time. Okay. We can prove all this using renewal reward. Okay. The proof of theorem 1. Suppose we start the chain at time 0 in distribution pi. All right. Let nj tilde t be the counting process of state j given we start in distribution pi. Okay. nj tilde t is simply a counting process. So, what am I doing? I am starting in distribution pi at a time equal to 0. What does that mean? So, at time equal to 0, the probability that I am in state I is just pi I, all right, and then I let the chain run and I am going to count the number of times state j occurs until time t, and I am going to call that nj tilde t, all right. Now, please note that probability that xn is equal to j is equal to pi j for all n greater than or equal to 1 and for all j in S, right. So, if you look at this guy, now consider expected nj tilde t over t, all right, that is just 1 over t sum over n is equal to 1 to t probability that xn equals j, right. So, you are looking at the, so you can look at this as maybe I should write 1 over one more step, right, maybe I should write it as expectation of the indicator, right. What is nj tilde t? Nj tilde t is simply the indicator that xn is equal to j summed over n is equal to 1 to t, right. Now, I can take the expectation inside because inside the summation, because this is a finite sum. So, and if I take the expectation inside the summation, I have the expectation of an indicator, and the expectation of an indicator is simply probability, right. So, this becomes 1 over t sum over n is equal to 1 to t probability that xn equals j, right. But of course, probability that xn equals j is simply pi j. So, this is pi j, correct. So, this is true for all t, correct. Now, you can condition on starting state I and use total expectation to write expected nj tilde t is simply equal to sum over pi I pi I expected n I j of t, right. So, why is this? So, nj tilde t is the number of occurrences of state j until time t, but you could have started in any of the states I, and the probability of starting in state I is by assumption pi I am starting in the stationary distribution, right. So, this is by total probability, right, the total expectations, the law of total expectations, right. So, this implies what? So, this implies an important equation. So, 1 over t, this implies expected nj tilde t is equal to 1 over t sum over I belongs to S pi I expected Nij of t, okay, for all t not equal to 1. So, this is an important equation. Okay. Let me call this dagger. Now I have to bound. So, but I know that, so the limit t tending to infinity of the left hand side is equal to pi j, right. So, that also I know. So, but let me do the following. So, this I know to be equal to pi j, but I will use that later. Okay. Maybe I should just write it down. So, this implies pi j is equal to 1 over t sum over I belongs to S pi I expected n I j of t. Okay. Actually, let me call this is true for all t greater than or equal to 1, all right. So, this let me call this dagger. Okay. This is an important equation. Okay. Now, you are looking at expected Nij of t, right. So, if you are starting at I and then you are looking at the subsequent occurrences of j, that is your Nij process, right. Now, if you are looking at some time t, all right, you can write expected. So, let me call this time as Tij, all right. So, it is the first time that the first passage time from I to j, okay. And then I am looking at a delay renewal process basically of returns to j, okay. Now, this expected Nij of t can be written as okay. So, let me condition on expected Nij of t given Tij equal to some t1, all right. So, I am taking this time to be equal to some t1, okay. This will be equal to 1 plus expected. So, you will have one occurrence of j and after which you are looking at Njj of t minus t1, right. So, you are conditioning on Tij is equal to t1 and then so Nij of t will simply be 1 plus Njj of t minus t1, correct. So, this is t minus t1, that is t minus t1, all right, and this is less than or equal to 1 plus expectation of Njj of t, correct. So, this is true for all t1, all right, and in the right hand side, so this is true for all t1 and in the right hand side there is no t1, right. So, this seems to be true for all t1. So, I can write expected, I can just remove the conditioning, right, and write expected Nij of t is less than or equal to 1 plus expected Njj of t for all t, all right. And this is true even if this t1 were to be infinite, this is still true, all right. You can easily verify that, okay. This equation will still trivially hold, okay. So, we have this equation which is nice, right. So, we can put this back into our dagger, right. So, then what happens? So, then I have sub back in this dagger, and then what happens? I will get pi j equal to 1 over T sum over I belongs to S pi I expected Nij of T, all right, which is less than or equal to 1 over T sum over I belongs to S pi j 1 plus expected N jj of T, right. This is true for all T. Now, what does this mean? I have T pi j is less than or equal to sum over I belongs to S pi j 1 plus expectation of yeah, that is right, expectation of Njj of T, right. So, this is pi I, sorry. So, this is the mistake I made, I think. Sorry, I made this mistake, my apologies. So, I made this mistake. So, now, yeah, so here this also should be pi I, all right. So, now if you look at this, this guy, this term has no I in it, right. So, this is just sum over pi I, which is 1, right, because I know that pi is a distribution. So, this becomes equal to 1 plus expectation of Njj of T, okay. Which means that I can write expectation of Njj of T is greater than or equal to T pi j minus 1, okay. This is true for all states j, okay. Now, since sum over pi I is equal to 1, pi j is strictly positive for some j, otherwise they cannot sum to 1, right. So, this implies for such j expected Njj limit t tending to infinity is greater than or equal to T pi j minus 1 and pi j is strictly positive. So, this becomes infinity, right, plus infinity. And this implies from our earlier theorem, if this limit of Njj t is going off to infinity, then this process is a legitimate renewal process. It implies that state j is recurrent, correct. And if you go back to the above equation, you get pi j. So, now you have proven that j is recurrent, you have to prove that j is positive recurrent, right. If you go back to this dagger, you have pi j is less than or equal to 1 over T plus expected Njj of T, right. This is just an upper bound on the dagger equation, right. This I know to be true, and this guy is strictly positive, right. So, this implies limit t tending to infinity expected Njj of T over T is strictly positive, right. Now, NJJT we already proved that NJJT is a renewal process, right. That is because state j is recurrent, we already proved the state j is recurrent out here. So, NJJT is a renewal process. Now, we are saying that limit t tending to infinity expected Njjt by T is strictly positive, but by elementary renewal theorem this is equal to the reciprocal of Tjj, right. So, this implies that expected Tjj is finite, implies j is positive recurrent, all right. So, not only is j recurrent, j is also positive recurrent. Okay. So, in fact, we can prove that 1 over tjj, expected 1 over tjj, right, which is just limit t tending to infinity expected njj of t over t, which is by elementary renewal theorem, is greater than or equal to pi j, right, which I know is strictly positive. In fact, this greater than or equal to, we will show, holds with an equality. Okay, that will be our next result in proving this theorem. So, just to recap, so I have proved that j is, I have followed the sequence of step, first proved that j is recurrent, all right, by showing that expected njjt goes off to infinity as t goes to infinity. Then I proved that limit t tending to infinity expected njjt by t is strictly positive, which means j is positive recurrent. Now, the entire chain must be positive recurrent because you have one irreducible class, right. So, you know that all the states in the same class must be of the same type. So, if j is positive recurrent, then the entire class must be positive recurrent. So, the DTMC itself is positive recurrent, all right. So, from this we can prove that the DTMC is positive recurrent, since the DTMC is irreducible. So, we got that the DTMC is positive recurrent, and we got this lower bound on expect 1 over expected tjj is greater than or equal to pi j. Okay. Now, we will show that there is also an upper bound. Okay. So, that pi j will be equal to 1 over expected tjj. Now, you go back to dagger, which says that pi j is equal to sum over, so 1 over t sum over I pi I, sorry, pi, I keep making this mistake, pi I expected nij of t. Have I written it correctly? Correct. All right. Now, I am going to just go from fix some state m, all right, and then I am going to go, the summation I am going to go to only till m. Okay. So, I have pi j is greater than or equal to 1 over t sum over I equal to 1 to m. Okay. I am just going to go to m. Pi I expected nij of t, all right. This is true for all m greater than or equal to 1. Okay. So, I am just fixing some, so I want to take some limit inside, so I am fixing some finite sum. Okay. The reason I am doing this is so that I can take, so take limit n tending to infinity. So, I can simply just take t inside, so that is perfectly legitimate. Now, take limit t tending to infinity. Okay. Then I will get pi j is greater than or equal to sum over I equals 1 to m. See, I am taking the limit inside this finite sum, which is why I took only finite m. Okay. So, pi j limit t tending to infinity nij of t over t expectation, expected nij of t over t. So, now we know that the state j is positive recurrent, right. So, this guy, this limit by elementary renewal theorem for delayed renewal processes, this will be equal to 1 over expected t jj, all right. So, this is equal to, so therefore, pi j is greater than or equal to 1 over expected Tjj times sum over I equals 1 to m pi I. Maybe I should say, again I made the mistake, right. So, I have to write I here, I keep making this mistake, sorry, sum over I pi, right. This is true for all m greater than or equal to 1. Okay. Since this is true for all greater than or equal to 1, m greater than or equal to 1, and so I can take m as large as I want, right. So, and then this guy will get as close to 1 as I want, right. So, since this is true for all m greater than or equal to 1, I have that pi j is greater than or equal to 1 over expected Tjj. Alright, because if pi j were less than 1 over expected Tjj, I should be able to take little m large enough so that this inequality above is not true, alright. So, I got this bound, right. So, I have this guy, let me call this 2, and I have already upper bound, isn't it? Where do I have that? This I have 1, right. So, I have 1 over expected Tjj is greater than or equal to pi j, and here I have 1 over expected Tj less than or equal to pi j. So, 1 and 2 imply that pi j is equal to 1 over expected Tjj, right, and this is true for all states j. There is nothing special about this j that I fixed. So, what have I proved, right? If I have proved that if there is a PMF pi I, if there is a distribution pi I which satisfies the balance equations, pi is equal to pi p and sum over pi I is equal to 1, then that pi I must be equal to 1 over expected Tjj. Okay. Therefore, pi j's are unique, right. So, whenever there is a solution pi j, that pi j must be equal to 1 over expected Tjj, alright, and this chain is positive recurrent. So, if you go back to theorem 1, I have proved theorem 1, right. So, I have proved this, I have proved uniqueness, and I have proved positive recurrence, right. So, I am done proving theorem 1.